Welcome back to Two-Phase Tuesdays. I'm your host, Lucas Beran, and appreciate you for being with us here today. Before we get started, I want to start by just saying a very big thank you to everyone who tuned in to our first episode. Industry contacts, colleagues, friends, and family. Really appreciate you joining in the conversation, adding comments, questions, providing us feedback. Definitely feeling the love from the first episode. So again, just appreciate you for tuning in and appreciate you being here today. So today we have a great show for you. But before we bring in our guest, I want to update you on what Accelsius has been up to this past month, because it has been a busy month for us. And the month actually started off with some pretty big news where we announced a strategic investment in Accelsius from Johnson Controls. So really feels like that solidifies our market position, validates what we've been working on, what we are working towards. So really excited about that strategic investment from Johnson Controls. Then just a few weeks later, we were at the Open Compute Project Global Summit in San Jose, where on the first day of that show, we announced general availability of our MR250, our multi-rack 250 kilowatt liquid cooling two-phase CDU. So very excited about that product. First show that we brought that product to exhibit on the show floor. And then we also actually won an award at the OCP Global Summit. And so the Futures Technology Symposium, we submitted a paper focused on an optimized two-phase thermal chain utilizing our CDU, some cold plates from some partners at UT Arlington, as well as University of Maryland, and then server integration with Celestica. And we actually took home the best sustainability paper. So really excited about winning that award. And then last and certainly not least, just last week, actually, we exhibited at our first NVIDIA GTC show up in DC. Great show, lots of energy. Always fun to get connected with NVIDIA as they're driving a lot of what is going on in the data center industry right now. So good to participate in that show with NVIDIA. But with that said, let's go ahead and bring in the guest and get the show started. Awesome. So today's guest, we have Akshith with us. Akshith, you mind doing a quick introduction of who you are and what you do at Accelsius?
Yeah, sure. Hey, everyone. I am Akshith Narayanan. I'm a thermal engineer at Accelsius. Been here about 2 and something years now. So it's been a minute.
Fantastic. Yeah, you're one of the OGs at this point.
I like to say that.
Awesome. Well, I know you're busy. I appreciate you being here.
I'm excited to be here.
Awesome. Let's jump right in. So first, I want to start with kind of your educational background and just walk me through what that schooling was like, and then kind of the ultimate inspiration for what inspired you to join or study about two-phase cooling.
Yeah, sure. So I've always been interested in like mechanical engineering and all of that, and did my undergrad in India actually. Mechanical engineering, the subjects that clicked for me were all the thermal related stuff. So I was like, okay, this seems interesting. Yeah. Came to Georgia Tech for my master's degree and worked on a pretty cool project there. So came in wanting something thermal related, wasn't really specific on what I wanted to do. And then I think I found the right professor in the right group. And then the project just came to me where it was a two-phase cooling approach on electric vehicle inverters. Yeah. I thought that's really cool.
Yeah. No, I the first time we kind of got to sit down together and get to know each other was in my electric vehicle. And so you got to tell me about that project then. Love, to hear more details about what you did there and kind of the outcomes and did it ultimately work?
Yeah, sure. Yeah. So the project was a DOE funded project, and the goal was sustainable cooling, right? Okay. And the idea was, what's the most efficient way we can get power out of these inverters? And in that space, there's a shift from your traditional silicon-based transistors to silicon carbide. Okay. And the big difference in the two technologies, being pretty simple, is that silicon carbide switches fast. So it switches on and off extremely quickly. And every time it does so, it puts out a lot of power. So the idea is you need a solution that's robust to handle that transient behavior of a chip and also pull the heat off efficiently. And the last thing you want in a car is using a conductive fluid to cool something and having issues with leaks and fires and damage. So the idea was to use a dielectric, and the most efficient way to use any dielectric is boiling, two-phase. So it was a pretty cool project where we took the modules itself, soldered them onto cold plates, and then ran a bunch of tests, designed custom plates for flow boiling. Okay. And we got to visualize the flow. So we used like a high-speed camera that captures like 50, 60,000 frames a second. And actually visualize the bubbles forming or nucleating.
Okay.
To be technical.
Yeah.
And then as they grow, observe the different regimes of flow boiling. So bubbly flow and then annular flow. And as the bubbles kind of go through the fins and escape, it was a really cool project. And I think the end goal was exciting as well because the conclusions we kind of drew were that your cooling efficiency was a lot higher with two-phase, and actually the thermal resistances that we were seeing are way, way lower than anything you've seen with traditional cooling methods like air cooling or even single-phase water cooling. So it was pretty exciting. So leading off of that, looking in the job market, I never really thought, is there like an opportunity to use two-phase in industry
how do I
today?
apply this? Yeah.
Right, because in theory, it's a cool project to do it for cars, but then you have to worry about actually getting a fluid in and running all the plumbing and everything. And then Accelsius showed me. I was like, oh, wow, it's like the same concept except on a data center level. So that's kind of the journey here.
I think a lot of people don't necessarily realize that, what we're doing at Accelsius is widely done in a lot of other industries already.
For sure,
And it's really taken proven technologies and applying it to the data center industry. And certainly there's challenges there, but, overcoming those challenges and developing solutions that provide both performance, ease of maintenance, and a whole host of other benefits that I'm sure we'll talk about today when it comes to two-phase cooling. So now that you are at Accelsius, tell me about your role as a thermal engineer and kind of what that looks like on a day-to-day basis.
For sure, yeah. So I own the cold plates. So essentially any heatsink design from the chip to the interface into the server back to the rack is what our team owns, the VSS team, Vapor Server Solutions, and my specific role is designing all the cold plates. So the cold plate design specifically for GPUs today, GPUs tomorrow, some R&D stuff for things down 5 years from now, 10 years from now. We're kind of the vision that we see as a company of where we want to take two-phase cooling. Yeah. And at its core, also doing a bunch of R&D on, taking the existing architecture and pumping up the power and seeing how high power can we get to dissipate off of this single cold plate. Outside of that, it's a startup. You're pretty aware. So there's like a lot of hands everywhere. So some in reliability, some in servers, some in CDUs. But for the most part, cold plates are what I do.
Yeah, it's good. It's good to be able to wear multiple hats at a startup because you're going to get asked to.
Yeah,
absolutely. So I want to kind of change gears a little bit and kind of dive in a little bit further, get into some of the weeds in terms of two-phase cooling, within the cold plate, within the server level itself, what that looks like, some of the benefits associated there. So I really just want to start with the cold plate itself. Yeah. Of course, there's plenty of single-phase direct-to-chip liquid cooling we see out there. We're seeing a lot of momentum on the two-phase direct-to-chip side as well. So I'd love for you to just start with kind of talking about the differences between single phase and two phase at the cold plate level and what's actually happening inside that cold plate as heat is being captured from those processors.
Yeah, sure. So pretty simply and broadly, a single phase cold plate is basically copper with heat sinks. A heat sink is just a bunch of fins that you arrange a certain way to get your maximum surface area to pull the most heat out of it. Single phase or any single phase based solution, your fluid enters, flows through these fins. As it flows over the cold plate, pulls heat from the chip and then exits warmer. So it's not changing phase, it's just entering cold, leaving warm, and you have a gradient across the entire plate. Now, the reason this works is water is kind of a magical chemical. It has like incredible heat transfer properties, so it's able to pull a lot of heat out of it. But it also has its disadvantages because when you're working with electronics, you don't really, your first thought isn't to use water. Yeah. It just happened to be the case in the industry because chip power scaled so fast we couldn't keep up, and we looked at a gaming computer and went, let's maybe do that on a server. So where two-phase differs is the actual cold plate architecture can be very similar in that there's an inlet, there's a forced flow through some fins. Specifically what we do is flow boiling. So for all intents and purposes, we're also forcing flow through fins as it pulls heat away from the fins. The big difference being it's isothermal, so it enters and leaves at the same temperature. It's just boiling to pull the heat away. So it's changing phase. And this active phase change is what's way more efficient than just heating a fluid. That's what we call the difference between like sensible heat and latent heat. Right. We use latent heat, which is pulling the heat using boiling. And that act is so much more efficient that we can get much better thermal performance at a chip level. Now, innovation as these chip heat fluxes get hotter and hotter, of course, changes. So you have these kind of crazy cold plates with jet impingement and like specific channels. And people are working on doing...
And that's on the single phase side, right?
All single phase, correct. Okay. All ultra thin cold plates that are 3D printed and all this innovation to get to that thermal performance. At two phase, we already start at a pretty good advantage, even with a base cold plate. So what an interesting test we did with Intel actually was take a single phase optimized cold plate and just run two phase through it.
Yeah, yeah. That's the universal kind of cold plate idea, right?
Correct, exactly. And what we actually noticed was we just had about 20 to 30% better performance. That's a white paper you can see published as well with the third parties. It's not like I just said something and you trusted me.
We'll link it in the comments here.
Right. And that was kind of the first step of realizing, okay, two-phase is already much more efficient at the cold plate with traditional architecture.
Right.
As we scale to these more complicated kind of thin film evaporation and additive manufactured ideas, the performance limitations are just, there are none, in my opinion. It just gets higher and higher. So at its core, I feel like that's a big advantage to two-phase. And the only difference in the cold plates, if you really think about a universal cold plate, is just the fittings and the materials used. Because at the end of the day, we're dielectric. So we have to look at compatibility with organic materials. And there are just some that work and some that don't. But for the most part, there's a wide area of well-known automotive chemicals that work with our refrigerants because we chose ones that are in the industry already.
Yeah, commercially
nothing that was
refrigerants.
made yesterday that was for this purpose. It was very used in other industries in the world. And there's like a lot of historical data in terms of compatibility that we have to back off of.
Okay, perfect. So you're on the VSS team working on designing those cold plates. So I'd love to hear a little bit about, when you have a new processor that gets announced or developed, kind of what happens when it's, hey, there's a new GPU or a new CPU hitting the market. What does that mean for you?
Good question. So there's two paths to this.
Okay.
Path one is the get a product out with current architecture that fits into our process. So the big difference there is we basically, every new chip has new mechanical mounting. Right. The size is different. The shape is different.
Okay.
So what we do is we basically optimize the heat sink and flow delivery for the die thermal design that they give us. So from these chip manufacturers, we'll receive like this grid that basically says, here are your hotspots. This is where the power is the highest. This is where the heat flux is the highest. This is where your kind of residual power is. And then we design the cold plate for that. Okay. And then we go with a design that'll kind of incorporate what we've learned from past cold plates and put into a server now. And at the same time, we're also looking at, okay, from this chip, based on the power levels we have, how do we basically double, triple the heat fluxes, build something specifically to be the most thermally efficient design, and then test that in R&D. And that basically lays the stepping stone for the next chip that comes out, and we go, okay, we've done this ultra efficient design for the previous architecture with like higher heat flux. Yeah. We'll then use this for the next chip that comes out because every time there's a new release, like the power doubles, the heat flux almost doubles. So.
Yeah. Okay. So, I mean, it really sounds like anytime there's a new processor, you have to design a new cold plate, but you can carry over your learnings from previous cold plates, similar types of things. And, given that there's new GPUs being announced every year, new CPUs being announced every other year, that's what I like to call job security.
Yeah, honestly.
You're an important man, and there's always work for you to be doing. I know that's true.
For sure. I think I look back to like when I first came here, and our VP of engineering, Jeff, when I was talking to him, he was like, there's one thing I'll tell you for sure that'll not change. You're never going to be bored here. That has been true.
Yeah. Okay. Good.
It's always been busy and fun.
I'd say that's true for me too. I'm not designing cold plates, but I'm having a lot of fun and definitely not bored. So that's good. And then, so from there, we design a cold plate, manufacture cold plates, and then we have to actually integrate them with the servers, work with the server OEMs to get them, on their servers so they can be enabled to use our two-phase cooling solution with our two-phase CDUs. So what does that server integration process look like?
So I think we work with these big integrators in the industry. So like your Unicom and Park Place. These are all integrators that have been doing this for years. We take our cooling solution as it currently stands. We use them to integrate the servers in-house. So that's where they, with their expertise in both applying TIM and having the right machinery to do so, they basically use whatever like latest oven or latest batch testing technique, apply each TIM where it needs to go, put our cold plates on, fasten everything down, and then bake it. If it's a PCM TIM, if it's a different type of TIM, do something else. But I think that's where that interface is between us and OEMs, is these integrators, essentially, Park Place, Unicom, and we work with them to basically give them instructions on how we assemble a server, and then they go on and do the actual integration. For these smaller deployments, though, especially starting on, we actually did them in-house. So we have our own deployment team, and I got my hands dirty too. It was definitely nerve-wracking as I put cold plates on. I was like, first of all, this is my design. I hope it fits. And then it was this chip is so expensive. I need to make sure that what I do is done right. So I have got hands on here. It has been terrifying, but also exciting. And I think as we get to those really large scale orders, we're going to work with big integrators.
No, that makes a lot of sense. And, to me, it's fun to get hands on. I've got to get hands on with products at various times. I've stayed away from the $30,000 or $40,000 GPUs. So I'll leave that in your capable hands because I don't want to be, lose a good portion of my paycheck for the year. So maybe just kind of now taking a step back, thinking about the future, where things are headed, and how we see Accelsius evolving and growing to kind of stay at that bleeding edge of the industry, bleeding edge of liquid cooling. And I think, it's hard to know what's going to happen in the data center industry because everything changes so fast. But the one thing I think we do know is that, heat flux and TDPs are rising. And so would love to hear from you kind of what you see coming down the pipeline in terms of increasing TDPs and increasing heat fluxes. Is it GPUs and CPUs, one or the other? What does the future look like there for those processors?
I think at least in the last 2.5 to 3 years, the CPUs haven't got much hotter because a lot of AI usage today is based on the GPU power. So you need the GPUs to basically train these models. I think when it goes to inferencing, things will change. But currently it's still very train focused. And because of that, your GPU powers are basically doubling or tripling every cycle. So you had like the Hopper architecture, 700 watts. We're already at Blackwell, which is almost 1400. And then Rubin's rumored to be 2300. It's just doubling the power each time. And exponents work funny in that way that doubling the first few times is not a huge increase, but doubling the fifth time is like 10 times as much as the first time. So I think these powers are just skyrocketing. And the key here throughout all this is being as sustainable as we can to the power we use. So a large part of that is just being able to use warm water coming into the data center, right? Because that's the most efficient way to keep these things cool is to be warmer than ambient to the water coming in.
Enable free cooling that way.
Exactly. And I think the biggest trick there is to make sure that whatever solution we develop, I think not just as a company, but as an industry, we need to focus getting there. And the easiest way to do so is just extracting as much performance as you can out of the most critical component. And in the entire stack up from this chip to chiller that we'd like to talk about, the chip to cold plate is your largest thermal resistance. It's always going to be. And the most savings you have on that is going to end up with you having the most efficient system overall. And I think that's where two-phase really ends up shining. And that's been kind of the understanding is as the heat fluxes get hotter and hotter, we as a solution, two-phase is just more competitive. We were less competitive at 700 watts. We are, because the heat flux is low, we are way more competitive at like 3000 watts. And I think as the industry goes there, I think it's going to be exciting to see how much more savings we can get.
And definitely we talk about a thermal wall where, two-phase goes from a nice to have today to a need to have tomorrow. And so certainly, something we talk about a lot here and are focused on building for that future that we see coming. And then I just briefly add something I'm hoping I see in regards to, the differences in TDPs between CPUs and GPUs. Obviously it's GPUs that are driving the adoption of liquid cooling today. One of my hopes is that, because these systems are getting packaged together, that of course you're going to liquid cool those CPUs as well. But as the industry continues to learn how to deploy, maintain liquid cooling infrastructure, that it makes it an easier lift to say, I'm going to liquid cool those CPUs and operate more sustainably, more efficiently, because I'm already liquid cooling these GPUs and I don't need to learn anything new to liquid cool these. That's just an infrastructure decision.
Correct. And I think already CPUs, GPUs are being liquid cooled for the most part. I think the more exciting path there is also looking at these 100% liquid cooled servers. So your DIMMs, your SSDs, your like voltage regulators. These are all like really low power components that still need some form of cooling. And I think the moment we eliminate air completely and go complete liquid is going to be pretty exciting. And I think in the industry, a lot of OEM server manufacturers are also talking to, I think, us and the rest of the industry as well on, okay, how do we liquid cool everything on this? We don't want any heat sinks. I mean, we don't want any air heat sinks. We don't want any fans. We want the whole thing to be liquid cooled, but also not immersion because that's hard to kind of fit into the data center architecture.
Absolutely. So next thing I want to talk out is maybe a little bit further out from here, and that's microfluidics. And there was that Microsoft announcement, about a month or so ago, where they announced that they were doing some testing with microfluidics, essentially etching microchannels on the back of silicon directly. That yielded a lot of questions for us and what that means for our technology. Can we do that? Is our technology needed if we start, using microfluidics on the back of silicon directly? And it's really fun when we have a team here that has already been researching that and working on that. And you actually just got back from Interpack where you presented some research that you'd been doing on two-phase microfluidics cooling. So would love to hear about kind of that presentation, what you talked about, and kind of what that research covered on two-phase microfluidics or on-chip cooling, direct-to-die cooling, whatever you want to call it.
Yeah, sure. No, I think the day that announcement came out, a lot of academia, historically academic people rejoiced.
Yeah.
Because it was a case of in academia you do all these crazy projects, right?
Yeah.
That you don't really know when industry is going to look at it and go, we should try this.
Yeah.
I think with microfluidics it happened way faster than we expected it to.
Yeah.
And I think that's kind of good because I think for the first time we're realizing as an industry that your heat fluxes are getting so hot. You need to think about these crazy technologies today
Yeah.
so that in a couple of years you can actually deploy them.
Right.
So in terms of microfluidics, there's a lot of research. There's a wealth of this stuff being done in academia already. You look
Okay.
at a lot of these research papers by big universities, it focuses on this. And looking at that, a lot of it is focused on two-phase because,
Yeah.
again, when you break it down to that level, you're going to be more efficient boiling a fluid to pull the heat than you are using single-phase. And
It just makes me personally nervous because you want to remove all the physical barriers
Right.
between your $30,000, $40,000 chip. Probably
Yeah.
going to be much more expensive at that time with the heat fluxes we're talking and the computing power that an individual one has. But to me, it seems like any tiny imperfection and you instantly short circuit and there goes your chip.
I think that's the last of the concern because even with die warpage being an issue already today,
Okay.
when you remove the cold plate, which is a 4 millimeter copper block that's going to spread your heat and
Yeah.
even your temperatures, and you just have your silicon and water going over, remember water gets hotter as it moves past,
Yep.
you're going to have an incredible thermal like gradient across silicon with no kind of neutralizing pillowing effect from a cold plate. So
Okay.
again, with two-phase, it's going to be isothermal. The whole thing's going to be the exact same temperature boiling. It just feels a lot more efficient. So, and again, we can debate on like the efficiencies, but I think the exciting part at Accelsius is we're very focused on that R&D side. So I think around a year ago, we thought, what if we run a thought experiment? We take a die, we mimic it with a copper block, we do two tests, we sky fins on one of them, and we keep the other one bare. So we're talking no heat transfer features kind of manufactured onto it.
Okay.
What would happen? And we took our refrigerant, we impinged it directly on the die, and we also floated through the fins, and it was kind of remarkable to see the numbers we got. So
Yeah.
from just the fins, we were able to see thermal resistances, if you can call it a thermal resistance because there's no cold plate and TIM anymore, it's just fluid to die.
Yeah.
It was like 0.003 to 0.005 Kelvin per watt, which means
Okay.
even at that 3,000 watt power load, you're only
Yeah.
about 8 or 9 degrees warmer at your fluid than you are at your chip. And then the other interesting thing we did was, okay, take just a bare copper die that's extremely flat, do no heat transfer augmentation, and just spray refrigerant on it. What would happen? And it's interesting because just the effect of blasting refrigerant onto the die in tiny jets because of the high velocity, we're able to pull so much heat off of that at a Blackwell power level, we're still only at about 0.03 thermal resistance, which is about what you see with today's cold plates.
Okay.
And I think that's something really remarkable that with no difference and just blasting a die directly with refrigerant, we're still already cooling it. And by growing fins on it or etching microchannels, the performance limitations are just gone. We're talking almost that near 0
Yeah.
thermal resistance, which
Yeah.
would allow us to use like 55, 60 degree facility water, which is numbers that also allow heat reuse. And this entire new arc of sustainability really opens
Yeah,
up.
yeah, absolutely. And that's what gets me excited about two-phase direct-to-chip cooling and really the benefits of latent heat that, because you're changing phase and you're not increasing in temperature, it just gives you the opportunity to, do more with that higher temperature that you can operate at. So yeah, opportunities for free cooling is certainly very exciting. So this has been a fantastic conversation, Akshith.
Yeah, no, it was fun.
I've learned a lot. It's been fun. Any kind of last words of wisdom for our viewers in terms of, hey, I want to learn more about two-phase. Any suggestions you have for them and how they could continue to educate themselves on the two-phase direct-to-chip liquid cooling technology?
Oh, no, sure. I mean, I think our marketing team has done a great job of filling all the work we do and putting it on a website.
Yeah.
So we have all the white papers we write. So I think a lot of us in the thermal team have been our master's or PhD graduates that we focus to write 1 or 2 conference papers every year, just so we keep going to academia, seeing what the latest and greatest is, and publishing it from an Accelsius point of view. And you can kind of see all of that on the website. And I guess apart from that, two-phase direct chip has been here for a while. So just a simple Google, and you're going to find so much stuff on this that I think you're going to be excited to see that. Why haven't we done this yet? And it's exciting that we're finally using this technology on something as critical as a data center.
Yeah, no, it's been a lot of fun to work to commercialize this technology with you and the rest of the team. And, excited to see what the rest of this year brings and really excited for 2026 as well. So thank you again, Akshith. Fantastic to have you on the show. Hopefully we'll have you back on before too long.
No, this is fun.
Awesome. All right. Thanks so much, Akshith.
Yeah, thanks.
Cool. That about wraps up the show for today. So thanks again for tuning in. We got a busy Q4 ahead here at Accelsius. But we will be exhibiting at Supercompute 2025 the week of November 17th. So please feel free to stop by, say hi, see what we're exhibiting. But in the meantime, feel free to let us know if you have any questions in the comment, like and subscribe if you're interested in getting updates when we do future episodes. We should have our next episode out in about a month. But until then, y'all take care. Thanks so much.